Hi, my name's Chloe Miller, and I'll be going over Lab 4, Circuits and Capacitors. For the purpose of this lab, there are two parts that we break down. Part 1 is being able to predict circuit behavior containing resistors, and Part 2 is being able to use multimeters to measure actual values of the conventional current and potential differences in circuits. For the fundamental principles, the loop rule, which was established by Kirchhoff's law, of which voltage of an entire loop must be equal to 0 in a closed circuit. Then there's the conservation of current, which is established by the node rule, where a current leaving must equal a current entering, as well as Ohm's law, which describes the relationship between voltage and current, as seen in the equation to the right. And finally, how RC circuits function and what capacitors and resistors do to affect the circuit. For the experiment, we used the circuit construction kit from Java, and for part 1, we created a circuit with 2 batteries, resistors, and ammeters to see how the principles of charge and energy conservation work in a series and how Ohm's law is used. Then a voltmeter is used to see how the potential differences are throughout the circuit. Then for part 2, we created an RC circuit and made observations of the current and light bulb when charging and discharging. Then we plotted a graph to see how the time-dependent voltage when discharged changed over time. To start part 1, we predicted the current from the given information and found using Ohm's law the current was equal to 0.0204 amps. And when we recreated the circuit, the ammeter read 0.02 amps, so the prediction was reported correct. When inserted in the reverse direction, the ammeter read negative 0.02 amps due to the change in current direction. Then we created an open circuit by inserting a voltmeter. We found the potential difference to be 3 volts because this reads the whole current, and the ammeter is 0 amps because there is no current flowing through the wire. For the final section of part 1, we found the potential differences for each part of the circuit. We measured using a voltmeter throughout the closed circuit and found the voltage between the resistors and the batteries, with -3 being the voltage of the battery and 0.959 voltage for the resistor of 47 ohms and 2.041 voltage for the resistor of 100 ohms. But as we know in the loop rule, the sum of the differences of the voltages around this loop must equal 0, and that is in fact the case here. In this graph, we show the charge progression throughout the circuit and how it ends up resulting back to 0. For the additional calculation for part 1, when a voltmeter is attached, the ammeter reading does not change because the measure of the voltmeter is the potential difference in voltage points, so it does not affect the current of the circuit. For the calculated resistance using Ohm's law, the following values are shown here, and as seen, the experimental values are pretty accurate with a small % error to our original values. With the addition of an anomer in parallel at the 100 ohm resistor site, the current does change from what it was originally. This change is due to a change in the junction at the resistor site. The adjustment of the current is explained by what is known as the node rule, which describes that at any given node or junction, the current leaving must be equal to the current entering at that location. For the start of part 2, we created an RC circuit and noted the observations with a 10 ohm bulb. When connected together, the light initially glowed, but quickly after dimmed out when the capacitor was charged. The current goes from the light bulb to the capacitor, but eventually stops through the current. Then we noted observations when discharging the capacitor. So when the capacitor was discharged, the light dimmed and eventually stopped glowing altogether. The current in this scenario without the battery goes in the reverse direction, capacitor to the light bulb, and this is due to the opposite orientations of the charges. Then the 2 different resistance of light bulbs were taken and then the time it took to take the charge and discharge of the circuit. The time values show nearly a double result from one another, which makes sense due to the doubling in resistance. The time for discharging also seemed longer than the time for charging in each bulb. Here we have a plot representing time-dependent voltage across a discharged capacitor versus time. From this data, we find a linear equation and use the slope of the graph, negative 0.145, to find the RC. Using the equation slope equals negative 1 over RC, we get RC equaling 6.89, which yields a 14.8% error from the expected value of 6 for the RC. For the additional questions, 1, if this lab was done in real life and contrary to virtually with an actual ammeter, the results would be lower for the current due to a higher resistance that would be present in the real ammeter. For the second question, if this lab was done as our ideal model, it would be expected that the capacitor would become instantly charged with the battery and no resistor present. However, in real life, it would not become instantly charged due to the slight resistance that exists in the current within the capacitor, wire, and battery. To conclude, the final results for each part were 1 being the total potential difference around the loop equaled 0 volts, which validated the loop rule of energy conservation, and 2 being the constant time value for RC was found to be 6.89 seconds, which yielded a 14.9% error from the expected value of 6. Overall, this experiment tested and reinforced physics principles that helped give a better understanding of RC circuits in a virtual and conceptual setting.